Welcome to my YouTube channel. Our topic today is uniform convergence of sequences and series of functions. We'll start by giving some definitions. The first is we want to define pointwise convergence. Let the sequence of function be denoted by f of nx. Then that sequence converges pointwise on A if for every element I pick in A, the sequence of real numbers converges to a point f of x. That is, when I pick a limit as n goes to infinity of that sequence of functions, I'm going to get f of x. I'm going to get a point or a function. Now, this function f is referred to as the pointwise limit of the sequence f of n. Another important definition is uniform convergence. Let f of n be a sequence of functions. We say that f of n converges uniformly on A if for any epsilon there exists an m such that n is always greater than or equal to m. Then the absolute value of f of nx minus f of x will be less than epsilon for all x in A. In other words, the rate of convergence of f of n to f of x does not depend on x, and there exists a single m that works for all x that is in A. Remark: the following result is a direct consequence of the definition and is worth taking note of. If f of n converges uniformly to f, then f of n converges pointwise to f, but the reverse may not be correct. So if once a function converges uniformly, automatically that function sequence of functions must converge pointwise. But a sequence of functions converging pointwise does not necessarily mean it will converge uniformly. The proof is left as an easy exercise. Let's take some examples. Show that the sequence of functions where f of x is equal to nx all over 1 plus n squared s squared for all x in R converges pointwise, but not uniformly convergent. Solution: here, we have to check for pointwise convergence by taking the limit of the function. And once you do that properly, you will discover that the function converges to 0 as we have it in our equation 1. Now we shall now show that the convergence is not uniform. Suppose that f of n is uniformly convergent in the interval ab, so that for all x in AB and for all n in K, this absolute value must hold. That is what uniform convergence says. So the function minus the limit point must be less than epsilon. So I have to prove that. Now, it is easy to see that with proper simplification that n is going to be less than epsilon over x in bracket 1 minus x when you make n the subject of the equation, the inequality. Thus, we arrive at a contradiction, and as such, see that the sequence do not uniformly converge in any interval AB with 0 as an interior point, even though it is pointwise convergent there. What is that contradiction we are talking about? We are saying from the definition says that n, we will always find an n that is strictly greater than or equal to m. But in this our result, we are having n that is less. So for that reason, we say no, this cannot work. That is the contradiction we are referring to. So for the function, sequence of function to converge uniformly, n must be greater than m. And the m in this our case is epsilon over x times 1 minus x. Now I have some tutorial questions here which you can practice at your own leisure time. Now, Cauchy's general principle of uniform convergence, an important theory in uniform convergence. to pointwise or uniformly. Now the theorem says a necessary and sufficient condition for a sequence of functions defined on a set to be uniformly convergent is that to each epsilon there exists an m such that for all n greater than m, for all p greater than 1, for all x greater than x, that this inequality must hold. Now this Cauchy general principle of uniform convergence is also left as an easy exercise. Let's take an example and see what it implies. Show that the sequence of function where f of n is equal to n over x plus n is uniformly convergent on 0k, whatever k may be, but not uniformly convergent on 0 infinity. Solution. We'll check for pointwise convergence first by finding the limit of the sequence of function. Now when you take the limit properly, you're going to see that the limit will be 1 for all x greater than 0. Therefore, the sequence f of x is pointwise, or it converges pointwise. And the pointwise limit is 1. Now we move a step further by checking whether it's uniformly convergent. Now let epsilon be positive be given. We have this inequality, the absolute value of f of x minus the pointwise limit of f, which is 1 in this case, is less than epsilon. Then we try to make n the subject. Now you're going to see that n in this case is strictly greater than x, multiplying 1 over epsilon minus 1. Obviously, m increases as s increases, so it is not possible to choose any number m such that for all n greater than m and for all s greater than 0, that this absolute value will be less than epsilon. Now if you observe closely, you will see that in this case we actually have n greater than m, but the challenge here is that x that is outside, as n is increasing, x is also increasing, and for that reason it will now be difficult to also find an n again that will be strictly greater than m. So that is where the challenge is. So this sequence of function converges pointwise but doesn't converge uniformly on the interval 0 infinity, because if you pick x to be very large, you also see that as n is getting large, x will also be getting large. Okay, but in a situation where infinity x does not take value from infinity or from a very large number, then now consider this interval 0k. We have replaced that infinity with k now, and is closed at k. So let n be an integer such that n is strictly greater than k, multiplying 1 over epsilon minus 1. We then see that for all n greater than or equal to m, and for all x in 0k, this absolute value will not be less than infinity epsilon, so that the convergence is uniform in 0k. Okay, so that is how it works. Another example, show that the sequence f of n, where f of nx is equal to x raised to power n, is uniformly convergent on 0k, where k is a number less than 1 and only pointwise convergent on 0, 1. Solution. The given sequence is pointwise convergent on 0, 1, and the pointwise limit f is given by 1 and 0. So the sequence converges to 1 if the range of x is from 0 but excluding 1. But when the range of x is 1, then it is 0. So in this particular example, the sequence of convergence converges to 2 different points. So we are going to check for uniform convergence on these 2 different points. Now let epsilon be given. Then for f of x equal to 0, we have the absolute value of f of nx minus f of x to be x raised to power n minus 0 less than epsilon. And when we try to make n the subject, we are going to arrive at n strictly less than the log of epsilon squared all over 2 log x. provided x is not equal to 1, because if x is equal to 1, it will make the denominator to be 0, and the whole problem will become indeterminate. Similarly, for x equal to 1, we are going to have x raised to the power n minus 1 less than epsilon, making n again to be the subject. We are going to have epsilon plus 1 all over log x, provided x is not equal to 1. We should know that, like x equal to 1, the sequence is not uniformly convergent in any interval containing x equal to 1, and it is known as a point of non-uniform convergence. So there does not exist an m such that for all n greater than m and for all x in 0, 1, this absolute value is less than epsilon. So in the two results we got, n is always less than, instead of being greater than. That is what we are looking for. Furthermore, suppose that k is a number such that k moves from 0 to 1, but 1 not inclusive. We can see that 0 to k, that n will become greater than log epsilon squared all over 2 log k, provided k is not equal to 1. And again, the second point will be n greater than epsilon plus 1 over log k, provided k is not equal to 1. Hence, we see that for all n greater than m and for all x in 0k, the absolute value is less than epsilon, so that the convergence is uniform in 0k. We need to look at a test for uniform convergence of sequence of functions. We are going to look at the MN test and the Weierstrass's M test, two of them. So what is MN test? MN test is a theorem which states that let f of n be a sequence of functions defined on an interval I such that the limit exists for all x, and that Mn, which is defined as the supremum of the absolute value of f of x minus f of xn minus f of x, such that x will be in the interval, exists, then f of n converges uniformly on AB, if and only if that Mn goes to 0 as n goes to infinity. If Mn does not go to 0 as n goes to infinity, then according to the Mn test, it does not converge uniformly. But once the supremum goes to 0 as n goes to infinity, then the sequence of function converges uniformly. So the proof is left as an easy exercise. Example. Let's take an example of how to apply the Mn test. Prove that the sequence of function where f of ns is equal to x over 1 plus nx squared converges uniformly on any closed interval I. Here, the pointwise limit is 0 when you take the limit as n goes to infinity. And when you now check for uniform convergence, which is the absolute value of f of x minus f of xn minus f of x, you're going to have x over absolute value of x over 1 plus nx squared. Now, we replace that inside the absolute value as y, according to the Mn test, where y is now x all over 1 plus nx squared. Now, from equation 3, you're going to differentiate. Remember, for us to get the supremum, we're actually looking for the maximum point or the minimum point of the sequence of functions. So from equation 3, you find the derivative. And when you find the derivative, for us to get the maximum point or the minimum point of the sequence of functions, you weight the first derivative to 0. Now once you do that, you're going to have that x will be equal to 1 over square root of n. Then you take the second derivative again and substitute x equal to 1 over square root of n. You're going to have minus square root of n over 2, which is negative or which is less than 0, showing that y is maximum when x is equal to 1 over square root of n. Now from equation 3, the maximum value is y equal to 1 over 2 times square root of n. Therefore, mn is the supremum of the absolute value of f of nx minus f of x, which is the supremum of absolute value of y, and which is equal to 1 over 2 times square root of n. Now, if you look at that mn, it actually goes to 0 as n goes to infinity. So according to the mn test, you say the sequence of function is uniformly convergent on the closed interval R. Let's look at another example here to show that the sequence of function where f of nx is sine nx all over square root of n is uniformly convergent on 0 pi. Pi there is 180 degrees. It's an angle. Here, when you take the limit as n goes to infinity, you discover that the sequence of function will go to 0. Then when you identify your y to be sine x nx over square root of y, and you take the derivative, you're going to have square root of n cos nx. And when you equate it to 0, you're going to have that x is equal to pi over 2n. Then when you take the second derivative, you're going to get equation 10, which is minus n raised to the power 3 over 2, and is less than 0. Because it's less than 0, the maximum point exists. It has a maximum. So showing that y is maximum when x is equal to pi over 2n, and the maximum value of y is equal to 1 over square root of n. Moreover, x equal to 2n goes to 0 as n goes to infinity. Now, going from equation 11, equation 8, and equation 9, our mn then will now be 1 over square root of n. And when you take the limit of that 1 over square root of n, you will see that mn will go to 0 as n goes to infinity. So according to the mn test, the sequence of function uniformly converges on the interval 0 pi. Let's look at another example. Show that the sequence of function where f of n is equal to nx times 1 minus x raised to power n is not uniformly convergent on the closed interval 0, 1. Solution. We are going to find the limit points, whether it converges pointwise or not. So when x is 0, the sequence of function is also 0. And when x is 1, the sequence of function is also 0. So the limit point is 0. So we have considered the endpoints, which is 0 and 1. Next is to consider the interval from 0 to 1, where 0 and 1 is not inclusive. Now when you do that, the limit of the sequence of function will also give us 0. Reason being that the natural log of 1 minus x will always be negative provided x is a fraction. So log of any fraction will always give us a negative number, and for that reason e raised to the power of a negative infinity will give us 0, and multiplying by infinity again will still give us 0. So everything boils down to 0. Therefore, the given sequence converges pointwise to 0. Hence, to check for uniform convergence, you will now move a step further by saying absolute value of f of nx minus f of x, where our y, to give us absolute value of y, where our y will be nx times 1 minus x raised to the power n. Now you take your derivative here, as seen in equation 13. When you take your first derivative and you equate it to 0, you are going to have that x will be equal to 1 over n plus 1. This is what you're going to have. Then you move a step further for a second derivative. When you do that and substitute x equal to 1 over n plus 1, you're going to have that our second derivative is less than 0, being negative. So for that reason, the sequence of function has a maximum at x equal to 1 over n plus 1. And from equation 12, the maximum value will now be y equal to n over n plus 1 times e raised to power minus 1. That is exponential. Equation 4, as seen in equation 14. Now our mn will now be n over n plus 1 times exponential raised to power minus 1. Now when you evaluate properly, you will see that mn converges to 0.369 approximately, and that figure is not 0 as n goes to infinity. So for that reason, we say that mn does not tend to 0 as n goes to infinity. Therefore, the sequence of function is not uniformly convergent on 0, 1. Next is a test for uniform convergence of a series, where we are going to use the theorem here, where stress M test for uniform convergence. A series, summation of f of n will converge uniformly in AB if there exists a convergent series Mn of positive numbers such that for all x in AB, the absolute value of f of xn is less than or equal to Mn. This is the Weierstrass's M test for uniform convergence. We also left the proof as an easy exercise. Let's look at this example on how to apply the Weierstrass's M test. To show that the series summation as n goes from 1 to infinity of sine nx all over n raised to power p, as p is strictly greater than 1, is uniformly convergent for real values of x. Solution. Let the sequence then be sine nx over np, and so the absolute value there will give us 1 over np, which we can say is equal to our mn for all x in R. How did we get the 1 on the numerator? The sine function has values between -1 and 1, and the absolute value of -1 or 1 is actually 1. So that is how we got that 1 there. It's bounded. The sine function is actually bounded between -1 and 1. Since the summation of mn is equal to now the summation of 1 over np, using our p series test, you can confirm that that series converges. So it converges uniformly for all the values of x using the Weierstrass's M test. I have another example here which says we should show that the series is uniformly convergent for real values of x. Solution. Let the sequence then be n plus 1 all over n raised to power 3 x raised to power n, and so the absolute value which will give us mn will now be the absolute value of n plus 1 all over n raised to power 3 x raised to power n for all x that is in R. Since this summation is equal to summation of mn is equal to the summation of n plus 1 all over n3 times n raised to power n. How do we check whether that series converges? We are going to use the ratio test first, where n will be n plus 1 over n raised to power 3 times x raised to power n, and n plus 1 will be n plus 2 all over n plus 1 raised to power 3 times x raised to power n plus 1. So when you apply the ratio test, which is taking the limit as n goes to infinity of an over an plus 1, this is what you're going to have. And when you simplify and factor out properly, you're going to discover that your end result will be 1 over x. Now, this 1 over x didn't give us much information, because if x is 1, according to the ratio test, is inconclusive. So for that reason, we are still going to probe further by using the rabies test. And the rabies test says the limit as n goes to infinity of n in bracket a n over a n plus 1 minus 1, if the limit exists. If it's greater than 1, then it converges, but if it's less than 1, it doesn't converge. So when we apply the rabies test properly from the question, we are going to get 2, and 2 is greater than 1. So by Weierstrass's M test, the given series converges uniformly for all real values of x. Thank you for watching.